to the cloud. I started these two problems. They're pretty important problems because each one brings kind of a little something different to the party, right? So the first thing that I would look at when it comes to number two is that absolute value that kind of strikes fear into the heart of people everywhere. And, well, not really. It's not that bad. It's just it's nothing like what we were working on. You know, I got a nice smooth curve here. This absolute value function is going to be a V-shaped curve. Well, if you could call it a curve. I mean, everything's a curve, but it's a V-shaped function. All right, so I'm going to type it in. F of x, oops, I need the x in the f of part, is equal to 2 paren x minus uno, close it up, minus 3, and lock it in. So it's a good looking graph, very, very vibrant looking, but it's something that kind of tells us that what we're about to do is not very meaningful, right? In terms of finding the slope of the secant, right? So we could try to do it algebraically, but we're actually not going to. I'll just show you f of 0. If I can remember where the f is. F of 0 is -1, and f of 2 is also -1. All right. So what that tells me is that at the x value of 0, I have a y value of -1. So I'll plot that point. At the x value of 2, I have a y value of -1 also. All right. And so what we notice here is the two bounds are actually on different pieces of the absolute value function. All right. Now, an absolute value function, in order to be what we call differentiable, it would have to be looked at as two separate functions. All right. One linear function on the left-hand side and one linear function on the right-hand side. So instead of having this equation in absolute value form, what I would do instead is write it as a piecewise function, right? So it would be f of x is equal to, now we have the benefit of having the graph in front of us. So I can pull out the slope and the y-intercepts and be in pretty good shape here. So I have a y-intercept right here, 0, -1. So that left piece would have an equation of -2, right? We get the slope from the x value, geez, the coefficient of the piece of the, you know what I'm doing here is I'm just saying words and hoping that they make sense in the context, and it's just not going well. The coefficient of the absolute value function, right? So this gives the slope all right, both of them, just one of them is going to be positive and the other is going to be negative. All right, this piece is going downhill, so that's going to have a slope of -2. So -2x minus 1, all right, because again, the y-intercept is -1. Why I tapped on it twice, I don't know. All right, the other piece is going to have an equation of 2x, or an expression that represents the equation, 2x, and then what you could do is project backwards from this piece of the graph and trace it on down to 0, -5. All right, that would give you a good sense of the y-intercept, because if you're counting off the slope in the opposite direction, it's going to get you to a -5. So 2x minus 5. We would just have to stipulate under what circumstances each piece is relevant. All right. There's other ways to do it, because in this case, you know, for this one, I could also have said, because we have a point here, I could also have said 2 times x minus 2 minus 1, you know, using the point slope form. All right. Either way, No problem, Tulio. I'll get you for attendance in a couple minutes. So if the X value in this graph is less than 1, less than or equal to, either way. I'll say less than or equal to. Then this piece would be relevant. If the X value was greater than 1, so getting onto this piece here, all of this stuff, starting at 1 and then going on forever. Now here, I could say or greater than or equal to if I want, right? The idea is that this would show an open circle at that vertex, but this would close that open circle. So it would be fine either way, all right? That would be the piecewise function that represents this graph. And I'll just show you really quickly. So if I type in each piece separately, and Desmos, you have to do it that way. It's annoying, but it is what it is. Y equals -2x minus 1. See, it maps directly over the left piece of the absolute value function. And then open a squiggly bracket and then stipulate the domain x less than or equal to 1. Right? It maps directly on top of the relevant piece. Right? So I could even turn this off and you see I have what I need for at least the left side. The other piece would be y equals 2x minus 5. Again, stipulating the domain where x is greater than 0, I'm sorry, greater than 1. Right? And so, it gets a little funky in terms of plotting of the points, but if you bring it in and you really look at it, you see it looks the way it should, even though it's not, for whatever reason, always reporting the best value. So, and the reason why is I stated here that x, it has to be greater than 1. So when I'm plotting the point at this end here, it's focusing on just the red and it's saying it's not defined. So the first point that exists would have to be a point that's immediately after the 1 point, or the one -3. All right. But if I do it here, it exists for both of them, both the left piece and the right piece. For this one, there's a point that exists because I defined it to exist at 1 -3. But like I said, this was optional. I could have made this a greater than or equal if I wanted to, and it would have been fine. And you see here, we have a defined point, turning point. So either way would have been okay. All right. So all of that is my way of saying that the slope of the secant in this situation would be meaningless. Right? Because they're not contained on the same continuous function. Even though you have this absolute value function that makes it seem like it's one straight function, it's really broken up into two separate functions. It's kind of like if you think back to quadratics and finding inverses and things like that. Sometimes you'd have an equation like y equals plus or minus the square root of x. It kind of feels like it's one equation, but it's really not. It's y equals the square root of x or y equals negative the square root of x. It's two separate equations, right? And so what's happening here, just write example there, is that we're looking at two separate equations that were put together to make one function. These are the two separate equations. Finding the slope from one equation to another doesn't have any meaning, right? So, because what happens here is the 0 would fall on this piece. Let me get a highlighter on the 0. And the 2 would fall on this piece. So yeah, you could technically compute a slope, but it wouldn't have any meaning. Okay. So that's good news, because that's the theory behind it. But what it's really telling us is that if you see absolute value functions, see if the two endpoints are on the same piece or on different pieces. Because if they're on the same piece, then it would have meaning, right? But that's something else to consider. Let's say, for example, we were interested in, I'll say, the x values of 1 and 2 instead of 0 and 2. And bring back the zoom the right way. I think 1 and 2 would work. Yeah, 1 and 2 would be fine. So let me say f of 1 which gives the coordinate 1, -3, and then f of 2, which gives the coordinate of 2, -1. All right, you see both of these points are on the same piece of the graph, so they're on the same line, which is great news. It means that you can find the slope of the secant. However, if you're thinking about a line segment that connects 2 points on a graph, in this case, there's no way for you to draw that line segment without it overlapping the line itself. And if you're looking for a slope, all you need to do is recognize what the slope is of that line and you have your answer. All right, so you would not need to do any of this stuff. You wouldn't have to use a special program. You'd have to say, or you'd ask yourself, well, what's the slope of this line? Well, this coefficient gives you the slope of that line. So your answer would just be 2. All right, so recognizing what kind of function you're working with is really important. All right, so definitely take the time to do that. So the question is this a hard rule for all absolute value functions, or are there exceptions? They're actually, in the case of linear absolute value functions, it's a hard rule. But in the case of other types of absolute value functions, there are exceptions, and we'll get to those down the line. Because you could take the absolute value of a quadratic or a cubic or something like that, and you'll see that there's different characteristics of each type of graph. All right, so I can just show you really quickly. If I were to take the function y equals the absolute value of x cubed, you look at this graph, it's smooth and continuous along pretty much everywhere. We would not write this as a piecewise function, and the rationale behind it has to do with the signage. All right, so if you're dealing with, and I could, there was a function on here that I have not quite, oh, there it is. I just learned how to do this, and it's really terrible because I thought I knew everything there was to know about Desmos. I clearly don't. Let me just show you that again. It's cool. I had no idea this existed. Right. So y equals, you put in your function. Because one of the nice features about a TI calculator is that you can access a table of values. So if you want a table of values for an equation that you type in Desmos, you hit on that little wrench thingy and you see an image of and the crazy part is right next to the duplicate function. I've been staring at it all this time. But you tap on that table and it'll produce a table of values for you. And you could expand this table of values if you want, but it'll still give you that table of values, which is kind of nice, right? So anyway, the result of this computation shows that all of the x values lead to positive y values, regardless of the sign of the x value. That's all well and good, but it's the points in between -1 and +1 that we care about, because in this case, if you zoom in And you could even pick some other points. You know, you could amend your table here. And say maybe you want to go and put in like a 0.001 just to see what the y value is. You know, you could do that, but the whole idea is to see if it ever comes to a point. If it comes to a point, then all this information here about the secant line having a slope that would be meaningless, it doesn't apply. All right. It's only when it comes to a point that we start being concerned with that sort of thing. So let me show you an instance where, how do I get back? I mean, I guess I could hit the back arrow. See, that's one thing. So I don't know how to do that. I'm not in love with this because, like, if I want to go back to the actual equation, you have to hit the back arrow, right? And that's kind of annoying. But if I wanted to make this x squared, all right, turn on my graph, absolute value of x squared, that's going to be fine also, because whenever you square an x or you square anything, it automatically becomes positive. The absolute value is irrelevant because everything's positive anyway, right? But if I take this and subtract from it, let's say 4. Oops, that's not a 4. Now I have a wildly different looking graph that comes to a point, all right? Because what happens in an absolute value equation, and it's really cool, and it's one of those things that you never really have time to think about as a student, but once you think about it, it makes all the sense in the world. You know, like an absolute value is taking something that's negative and making it non-negative, right? So a -2 becomes a +2, a -7 becomes a +7. That's all well and good, but if you consider that it shouldn't be any different if you're talking about the graph of functions, then that kind of opens the whole world. Because let me show you what y equals x squared minus 4 looks like. So x squared minus 4 has a good chunk of it, an infinite amount of it above the x-axis, and then just a chunk from -2 to 2 below the x-axis. All right. So if you look at the y values, because the y is what we're concerned with here, all positive, all the y values are positive regardless of the x value until it gets past that -2 threshold, at which point all the y values become negative until it gets to the +2 threshold, in which case all the y values go back to being positive. So what an absolute value is doing to a function is it's taking the negative parts of it and making those negative parts positive. So it would take this part of the graph, all right, this interval of the graph, and reflect it over the x-axis, right? So that's what's happening here, all right? It's just a reflection right over the x-axis. That's why it comes to a point. And the same would be true for a trig function. So if you have like y equals the sine of x, you got parts above, parts below. But if I say y equals the absolute sine of x, you look at it and everything that was negative has now become positive. Everything that was positive remained positive. All right. So when you kind of shine that light on it, you realize, oh, these absolute value graphs aren't really as difficult as I thought. If I know how to create an ordinary graph, I know how to create an absolute value graph. All right. So, you know, hopefully you found that to be helpful. I found it to be really enlightening, which is kind of crazy because it was self-enlightening because nobody ever told me that. I just noticed it one day, and then everything just kind of fell into place. I was like, oh, that's pretty cool, you know. So I figured I'd tell everybody that every chance I can get, you know. Number 3, f of x is equal to x minus 1 times x squared minus 4. So in the same vein as all this other stuff, I'm making a lot of use out of Desmos today. What I'm going to do first is take a look at the picture. I'll just call it y. And I'm going to make sure that the two pieces or the two x values that I'm looking at actually fall on the same piece, right? Because we're looking at asymptotes here, all right? So we'd have an asymptote at x equals -2, and we'd have an asymptote at x equals +2. I gotta get the right function here. Come on. I don't know why it does that. It just thinks I want to copy the whole page, but I don't. All right. So these are disconnected, discontinuous pieces of a graph. So at 1, I'm looking at a point that's on that middle piece. So this whole piece right here. At 3, I'm looking at a piece that's over in this neighborhood. All right. So this goes hand in hand with what we were talking about over here. The slope of the secant in this situation would be meaningless, right? Because there is no connection between those two pieces. So finding a slope, an average rate of change over those two intervals, it's apples and oranges, all right? So for the same reason, because of, same but different reason. You know, the last one had to do with the fact that it was two distinct functions being pieced together, coming to a point. But in this case, it's a discontinuous function. So due to discontinuity over the given interval. All right. So it's one of those reasons, or one of the main reasons why we talked about discontinuity. It's very important because it saves you from spending time unnecessarily on a problem when you don't need to. I suppose that's the definition of spending time on a problem unnecessarily. Right? But anyway, if you're concerned about getting more practice with actually finding a slope of the secant, don't worry, we're coming to it, because we're going to talk about instantaneous rate of change. So slope of a tangent line at a point. All right. So a tangent line is a line that intersects a curve at exactly one point. All right. So if we have an arbitrary curve, a tangent line would look something like this. Let me just get it to actually touch and we'll be good. So this is an example of a tangent line. And so this would be the point of tangency. So what we want to do is come up with a method by which we can determine the slope of that line. All right. What we would run into as an issue, you know, a little different from what we talked about last class, is if we wanted to find the slope between a point and itself, we end up with something that's indeterminate. All right. So if I tell you that this point has coordinate, we'll call it just xy. It's a variable coordinate. It could be at any point along the curve. All right. If I tell you that point has coordinate xy, then its slope would be, well, y minus y over x minus x, 0 over 0, and that would kind of defeat the purpose. All right. Well, and actually, I'm crossing that out because it's irrelevant, not because it's incorrect. It's a correct statement. It just it leads us to kind of an issue. What it tells us is that we can't take, or we can't determine the slope from a point to itself. But what we can do is start off with some arbitrary point off in space over here, find the slope connecting our starting point and that other point. All right, so that would be the slope of the secant line. I just gotta fix it a little bit. Oh, come on. All right. Alternatively, just move the point. So we could do this. I mean, that would give us an estimate. It would be a poor estimate. Okay, so this would be a secant. All right, maybe we could move that point closer. Actually, let me draw the line first here. I'll do it. Yeah, maybe I'll just go right to here. This would be another secant. Also an estimate, not a good estimate because our tangent line clearly has a positive slope. It's going upwards. These are going downwards. But if I get close enough, so let me put a point like over here, I can start kind of zeroing in on what the slope ought to be. Yeah, right. This is going to be a more accurate estimate, right? So if I could bring this point even closer and closer and closer, moving inward towards that initial point, I'm going to get a better estimate of what that slope of the tangent line would be. Right? The issue is I can never actually get to that point, that initial point, because if I did, I fall into this trap. Right? But what I could do is I can make my second point get closer and closer to the first point so that it's infinitesimally different. Right? So it's only a smidge away. So I can steal some of the work that we did on the previous page. We could take the slope of the secant formula, which is f of x plus h. We've got a couple variations, but this is the one we're going to focus on for now, minus f of x over h. And instead of just computing the slope between 2 points, what I'll do is I'll take that relationship and say, okay, well, what would happen if I found the limit as h approached 0 of this expression? Because remember, h is referring to the horizontal distance between the 2 points. So if I tell you that the horizontal distance is approaching 0, what I'm telling you is that those 2 points are getting closer and closer together. Right? So we can't determine what would happen if the horizontal distance was equal to 0, but we could determine what the slope would be as it trends towards 0. All right. It's along the same lines of limits where we would say, well, you don't actually have to get there. You just have to know what the result would be if you could get there. All right. So it's that concept of infinity. So this is the slope of the tangent line. All right, and we'll do this again with the alternate formula, but that's in a little while. All right, so what if they were different intervals? It depends on what you mean by that. If you're talking about what we were looking at over here, where you have a value, for example, a 0 that fell in one interval, so one piece of the piecewise function, and another that fell in the other piece, then the instantaneous rate of change wouldn't have the right kind of meaning. So we'd have to make an adjustment. We'd actually only focus on points that are on the appropriate piece. Right. So if I said find the slope of the tangent line when x is equal to 2, then I would only focus on this piece of the piecewise function. Right? So you'd have to be strategic in terms of your domains, which is one of the reasons why we always talk about domain. You know, the last two courses coming into this one, there's conversations about domains, and it's like, oh, we're always going to talk about domains, I guess. You know, so that's the idea. Example 4. That's actually a bad one. That's a bad example. It's a typo because I used to have a different example 3, and this is referring to the old example 3. So this one shouldn't even be here. So let's make this example 4. Find the slope of the tangent line to x squared, y f of x equals x squared, minus 4 when x is equal to 1, and then what's the equation of the tangent line? So we got a fair amount of work to do here. So first thing I'm going to do is grab my difference quotient or slope of the secant line, f of x plus h minus f of x all over h. Got a little extra schmutz there that I don't need. We know what f of x is. It was given to us. I just need f of x plus h. I need this piece. All right. So f of x plus h is what you would get if you took your original function and replaced every x with an x plus h. No, I already have the parentheses. Come on. All right, so that's what f of x plus h is equivalent to. We'll have to expand that out, but that's the long and short of it. So I'm going to put that into my difference quotient. X plus h squared minus 4 minus parentheses, my original function. I'll use this orangish color here, which is x squared minus 4 all over h, poor quality h. I'm going to zoom in here because my handwriting is going to not a good place. All right, so we'll distribute out the x plus h squared. That's the same as saying x plus h times x plus h. I got the minus 4. I'm going to distribute through this negative 1. So minus x squared plus 4 all over h. But the elephant in the room is this piece here. We'll have to distribute that out. All right, but I can cancel out the negative and positive 4, so that's something. Call that a little win. So x squared plus xh plus another xh plus h squared minus the x squared that's already there over the h. All right. We have some like terms. We have some opposites. Opposites can cancel. What we would end up with here as a slope of the secant line would be 2xh plus h squared over h. All right. We have a common h that can be factored out. And so our final answer for the slope of the secant line would be 2x plus h. All right. So that's, again, the slope of the secant line, not the slope of the tangent line. We're not quite there, but we're like half a step away. right? So again, slope of the secant line. If I want the slope of the tangent, all I'd have to do is take this result here, the 2x plus h, and find the limit of that as h approaches 0. Right. The idea again being that what we came up with, the 2x plus h, is an expression that represents the slope between any 2 points, any 2 distinct points, points that are not the same on a curve. What we're doing here is bringing those 2 points closer and closer together, or really the second one closer to the first one, and seeing what the slope would be if that distance ever got to 0. Right? And what we will end up with is a 2x. And so that's our slope of the tangent line for any x value. All right. So what this represents is the slope of the tangent for all x. All right. So on this function, and you know what, let me just get a fresh Desmos involved. This function f of x is equal to x squared plus, minus 4. We have this equation, or will be an equation in a second, that represents the slope of the tangent. All right. So what we would represent this as is we would call this f prime of x. All right. This represents the slope of the tangent line. So it means the same thing. This is the notation that we use. There's also another type of notation. We could use dy over dx, but I haven't really explained any of that form of notation yet, so I'd probably shy away from that at this point. So f prime of x represents the slope of the tangent for all values of x. All right. That slope of the tangent is also known as a derivative. All right. So that's a derivative. So what I want is the slope of the tangent when x is equal to 1. So what that's telling me to do is evaluate my derivative function for when x is equal to 1. It's the same as evaluating any other kind of function. Replace all your x's with whatever you're evaluating in terms of, in this case, a 1, and you get your result. So in this case, a 2. All right. So this gives us the slope of the tangent line when x is equal to 2. Oh, that's a big eraser. All right, so now I know what the slope would be at, let's see, 2, 0. So if I traced a line in such a way that it intersected just at this point, that line would have a slope of 2. All right. So at the value of 2, or at the x value of 2, we have a y value of 0. So if I want the equation of a line passing through that point, so the equation of a tangent line, I would use the point slope form, y equals m times x minus x1 plus y1. but I would actually modify it to be consistent with the notation that we're using here. Right? So it would actually be y is equal to f prime of a times x minus a plus f of a. Right? Where a is some constant value. So I have, if I assume that the a value is equal to 1, so I would call this my a. F prime of a, we've already figured out, is 2. X minus that a value, so x minus 1. And on Desmos, just by visual inspection, we figured out that f of a, the y value when x is equal to a given number, that was equal to 0. So plus 0. And that would be equal to my tangent line. So I could actually just type that in, y equals 2 parentheses x minus 1 plus 0. However, I must have screwed something up because that is, as they say, not even remotely correct. Oh, slope of the tangent when x is equal to, you schlemingo. X is equal to 1. 1 gives it 2, and 1, I was looking at the wrong point the whole time. So that's 1 negative 3. Oh, dingus. A little bit better. Yeah, I had the wrong point. Sorry about that. So yeah, this has got to be a minus 3. And everything was going so well. Right? Yeah, so you find the slope. The slope we did everything involved in the derivative correctly. I just screwed up the algebra 1. Right? So the coordinate that's relevant, because it says when x is equal to 1, for some reason I latched onto this number 2 and I just kind of wouldn't let go. But yeah, the a value is 1. And so that returns, if I plug in a 1 to this function here, that would return a value of negative 3. So that's where this coordinate comes from, which gets put in here and here, right? So, and you can see it's definitely a tangent, right? But what we want is something that's going to work in all cases in terms of the calculator. So, first thing I could tell you is that the calculator will graph the derivative function for you. It won't tell you the equation, but it'll graph it for you. Right. So all you have to do is type in f prime. You can do this on the keyboard, just an apostrophe. But if you look right next to the enter key, you can see, the comma key. But if you hit the up arrow, that comma becomes an apostrophe. Type in f prime of x, and it'll graph the derivative function for you. Right, which is wonderful. Problem is, it's not giving you the equation. All right. So how do you get? And when I mean equation, I kind of mean it twofold. It doesn't give you this equation, as in the equation of the derivative, but it's also not giving you the equation of the tangent line. Right. So we kind of want to make it do more for us. Right. So first thing I would do, I get rid of all this stuff. I can leave that. I would establish some point A, and I'll let A be equal to 0, just as a placeholder. And then I would establish a coordinate in general terms, A comma F of A. And this will be up on Blackboard later if you want it. All right. You put a label there if you want. It's a good idea to have a label because then it'll give you the points. If you just put A comma F of A, it'll plot it for you, but it won't tell you what the point is. Now, if I slide my slider, it'll move that point along the graph, which is really good. And by the way, I kind of like this a little bit better than, you remember I was showing you before how to make a table. I kind of like this a little bit better because you just kind of get what you need out of it. So it's just a thought. Anyway, so we have our derivative here. One thing that we can always kind of fall back on is the idea that calculators understand what they're programmed to understand. And that is notation, order of operations, notation and order of operations. So I asked this calculator to compute, or given a function to compute ordered pairs, so coordinates, and then also a derivative and plot it. Maybe I don't want the plot, so I can turn that off, that's fine. But I can type in this equation here, y equals f prime of a So that'll actually give me the derivative at a particular point. So if I move my slider over to just a 1, which was the question that we were being asked before, it would give me the 2 that we came up with here. That's great. Right? I want more, so I'm getting a little greedy. So open paren x minus a, then plus f of a. Right? So what it'll do for you is plot the equation of the tangent line. But you run into, it's the same issue. You run into the symbolic form versus the graphical form. So you want the symbolic there given the graph, right? But you can get an idea of what the tangent line ought to look like. You'll have the coordinates along the way, right? So you have the a and the f of a on this. I don't know what I just hit. I just hit continue. That's like something I don't even know, right? So you have the coordinates, the a and the f of a on the screen. So really all I would need is f prime of a as a standalone computation. And I would have everything I need in order to actually physically write the answer. So if I move my slider over to the given a value, they told me 1, so I move it over to 1. If it'll stay. Okay, it's locked in. Now I go down, I see my derivative should be 2. All right, that's true, I got that right here. Then below that, I see my equation is plotted correctly with coordinates 1, -3. So I put my 1, my -3, and I have everything I need, right? Just by creating a quick Desmos. Now, the benefit of doing it this way is, let's say I have another problem. Let me steal this one over here. X cubed minus x. Let's say I wanted to find the derivative at, the same coordinate at the x value of 1. X cubed minus x. I have it set to 1. It plotted my point 1, 0. It plotted my tangent line. It looks good. It's only, I only care about it being tangent at the point of tangency. The fact that it intersects the curve elsewhere is irrelevant, right? But I have my derivative, which would be 2 at the a value of 1. I have my coordinates, so I could easily write the equation of a line. It would be y equals 2 paren x minus 1 plus 0. And the good thing about this is once you get all that information, you have a way of checking it. Turn them both off, turn them back on one at a time, make sure they go to the same place. All right. So that's pretty nice. So I'll make sure I save this one up there for you. This is a equation of tangent line. That's not how you spell equation. And I'll get that on Blackboard for you so you have it. All right. pretty sure I have another version of it from last year, last semester, but I honestly don't remember where it is. So at least I have this going. Now, normal to a curve, equation of a line perpendicular to the tangent to a curve at a given point, right? One thing that you'd have to remember here, perpendicular lines have negative reciprocal slopes. So when they ask you to find the normal, you're actually going to do it in a very similar fashion to what we did, except once we find the slope, this computation, we're going to take the negative reciprocal of whatever that result is at the particular point. Right? So we're going to start this one from scratch, slope of the secant line. I have my f of x. I need the f of x plus h. Right? So again, that's what you would get if you replaced every x in your original function with an x plus h. So this whole expression is going into my difference quotient, and then it's going to get expanded and then cleaned up and simplified and all that. All right. So 9 minus 3 parentheses x plus h plus x plus h squared minus my original function 9 minus 3x plus x squared all over h. All right, so a little distributive property, a lot of distributive property. So 9 minus, so this negative 3 is going to get run through. 3x minus 3h plus, well, asked and answered. We already figured this one out. It's x squared plus 2xh plus h squared. Then I'm going to run through with this negative 1 here. So minus 9 plus 3x minus x squared. A little trick of the trade. Not really a trick. It's more like something to be on the lookout for. Your f of x should cancel out completely. If it doesn't, you made a mistake. All right. So that expression that you started with, that the one that I have here in orange, that should cancel out completely. If it doesn't, then you made a mistake somewhere. All right. So I have a 9. I got a negative 9. I got a negative 3x. I got a positive 3x. I got a positive x squared. I got a negative x squared. Cleans up beautifully. The negative 3h plus 2xh plus h squared over h. All right, we have a common factor of h. Negative 3 plus 2x plus h all over h. Cancel my h's. And now I have my slope of the secant as negative 3 plus 2x plus h. So what we learned in the previous problem is that all we have to do is slap a limit as h approaches 0 onto that. And we'll have our derivative. All right, so if we evaluate this for where h is equal to 0, we get negative 3 plus 2x. So that tells me that f prime of x is equal to, already that's 2x minus 3. All right, so that's my derivative. That I can verify. using the app, geez, not that fancy. I was going to say the app that I just created. I didn't create the app, I just created what's on it. Okay, so my original function, do a standard zoom. All right. So what this is saying is that my derivative f prime of x is equivalent. So let me get rid of all the other stuff. Oh, I got rid of the wrong thing. F prime of x should have an equation of 2x minus 3. So let me bring it in. Y-intercept, -3, check. Count off the slope. Let's see, it goes from -3, 0, -3 to 1.50. That's not nice. This one's a little nicer. 1, -1, if it'll stay on. Well, you believe me, it's 1, -1. Right? So if you're counting boxes, that's a slope of 2. You're going up 2 over 1. Right? So we have a slope, we have a y-intercept, it checks out. So what I would do now is find the slope of the tangent at x equals 0. So what that would be is f prime of 0. The reason why it's 0 is because that's what they said right here. All right. So I could use my slider here, go right over to a 0. If it'll let me, it'll let me. There we go. We're going to get a -3. All right. We're looking at the f prime of a. So then if I want, and so this is the slope of the tangent. The slope of the normal is the negative reciprocal of f prime of whatever your a value is. So -1 over f prime of a. All right, so this is my f prime of a because we're saying that this is the a value. So my new slope is going to be -1 over -3, or just 1/3. All right. So it's saying find the normal. The normal is talking about a normal line. So it's calling for the equation of the line. So not just the slope. So my equation of the normal line would be in the form of y equals, really the only thing that's going to differ is the slope because the point will be the same. So y equals -1 over f prime of a times x minus a plus f of a. All right. So let's get the coordinates of the function itself at that location. So let me go bring back the ordinary zoom here. At 0, we have a y value of 9. And just slap on this new slope. Right? That new slope is 1/3. So our final answer here would be y equals 1/3 x minus 0. You can just write x plus 9. I could even amend this to say, here's my slope of the tangent line, or I'm sorry, the equation of the tangent line. And then here I would say that this is the equation of the normal line. And then just do a quick duplicate of this bad boy, slide it down, and just tuck in a 1 divided by f prime of a. Get rid of this other f prime of a. and that would be the equation of the normal line, right? Mission accomplished. Scale-wise, it's not too pretty, but it gets the job done. So we'd have a tangent line. I'll get rid of the derivative, tangent line and normal line. The thing about the normal line that's kind of annoying is that, oh, sorry, apologies, -1. I just missed the sign for some reason. It doesn't always look like it's perpendicular, but especially on a TI calculator. But if you really bring it in, it does look perpendicular more and more because of the square aspect. You really got to kind of turn your head and just forgive any sort of imperfections. But I find that the grids and the axes can be distracting. So worst case, I just turn everything off and have a look. Oh yeah, that looks perpendicular. You know, then I just turn everything back on. So, you know, it can be a little annoying, but it's better than, you know, the whole lot of nothing that we came into this class with. Right? Tangent line and normal line. I got to work on the grammar on that, but I'll get there. All right, I'm going to check the old Chatterooski here. So whenever the slope of the normal is asked, it is the negative reciprocal, correct? Every single time. So when I ask for the normal, we find the tangent slope, find its negative reciprocal, and we have the normal slope. Right. So this next question, I always regretted this title. It just aggravates me. I'll take it as a typo. Right. It bothers me every time I see it. I've been meaning to change it forever. What about piecewise functions? All right. I always hated when textbooks tried to be like conversational. It's like, why are you doing this? You know, so this is, I'll just say piecewise functions. All right, so whenever you're dealing with piecewise functions, we're going to find the tangent of each piece, right, at the given endpoint. And if those tangents are the same, then the function is different, what we call differentiable at that point, right? So the issue that we're dealing with is piecewise functions can sometimes have discontinuities, can sometimes come to a point, you know, like an absolute value function, right? What we need to have happen is, in order for a function to be what we call differentiable, or I like to say derivativable, we need to make sure that there is no contradiction in slopes at any point. All right. So I'm going to give you a piecewise function because for whatever reason, the one I had here didn't show up on my PDF. So I'm just going to make up one. All right. So let's say we have f of x is equal to x squared if x is less than 0. Just making sure. Yeah, that'll work. And then I'm going to say 5. No. 0 if x is greater than or equal to 0. Yeah, that'll work. So we have the two pieces. We're going to look at them as two separate functions. All right. So we could use subscripts if we want, or we can just write them as y equals. But what I tend to do is just say f sub 1 of x is equal to x squared for my first piece. That's what that 1 represents. F sub 2 of x is equal to 0. All right. And so we would look at these as 2 separate problems. We'd run through the difference quotient for both of them. All right. So it's pretty simple now. I mean, it seems like, oh man, we're going to do that whole secant thing again. It's actually not that bad now because, again, if we're looking for f of x plus h, we're just taking an x plus h and popping it into the original function everywhere we see an x. So the fewer instances of x, the less we have to substitute in. So it would be x plus h squared minus x squared over h. I'm just going to move that over there. We know that when we distribute out the x plus h squared, it becomes x squared plus 2xh plus h squared. We have the x squared for the f of x. And the whole thing's over h. Common x squares will cancel. So we'd have 2x h plus h squared over h with a common h that can be factored out and canceled. All right, so h, 2x plus h over h with the cancellation occurring. And so that would be my slope of the secant. So then if I want my derivative, I'd find the limit as h approaches 0 of 2x plus h, and that would be equal to just 2x. So that's my, well, this I'm calling f prime, f sub 1 prime of x would be equal to 2x, because that's the first piece of the piecewise function. All right. Now, the second piece, that's a little bit more. All right, just got a little cough here. A little water. I think it's a reflux that's getting to me. I'm gonna put that out on YouTube, I guess. So the second piece is a horizontal line. All right. So if I'm looking for the slope of any 2 points, connecting any 2 points on a horizontal line, it's going to have a slope of 0. All right. If I'm looking for the slope of a tangent line, the thing about a horizontal line is there's no way that you could have a line that's tangent to that line in such a way that it only touches it at one point. You can't have one line touch another line at one point and be tangent to it without also touching all the other points. All right. So what we get at is the idea that the derivative of any kind of constant is always going to be equal to 0. Right. And I could show you really quickly, just using the calculator here, pop in a 0. For any a value, the y value is going to be equal to 0. The derivative is just a flat out 0. And you see how we have no difference between f prime of x and f prime of a? What that's telling me is that it doesn't matter where I put my slider, it's always going to have a value of 0. My tangent line is always going to have a value of 0, because if you look, it's right on that x-axis. All right. So without doing any work related to this, you could use a little, we'll call it calculus sense, and say f prime of x is going to be equal to 0, or for the second part of the function. All right. So now what I want to do is see if at these endpoints here for the first piece and the other, 0 in both cases, we have the same slope. If we do, then we're looking at a function that is differentiable, right? Because it's already going to be continuous, because f prime of 0, f of 0 for each piece is going to be 0 no matter how you slice it. They do connect. I'll show you that in a minute when I actually sketch this whole thing out. But my derivatives are also going to be equal to 0. So f sub 1 prime of 0, 2 times 0 is equal to 0. And f sub 2 prime of 0 is equal to 0 without any substitution, because it always has to be equal to 0 because that's the relationship. All right, because these two things are the same, we would say f of x is differentiable for all x. All right, so let me show you the sketch. So I'll get a fresh new Desmos here. So I'll put the original function in. We'll say y equals x squared, only over the appropriate interval. So where x is less than 0. And then y is equal to 0, but only over the appropriate interval where x is more than or equal to 0. We'll make them a little thicker. All right, so this is what our graph would look like. You could see that they're definitely connecting at 0. One of them has a less than symbol, but if I evaluate my first equation for when x is equal to 0, I get a y value of 0. It's going through the origin. If I evaluate my, with an open circle, if I evaluate my second equation for when x is equal to 0, it's going through the origin with a closed circle. Closed circle trumps open circle. So we have a connection there. Right? So there's no discontinuity. Now, all we'd have to do is look at our derivatives and see what's going on there. All right. So since the slope for the left piece at 0 is the same as the slope for the right piece at 0, there is no contradiction in slope. There will never be a contradiction within a function, a smooth continuous function, unless it comes to a point. You know, like those absolute value functions I was telling you about before, but even those can be represented with piecewise, right? So if there is no contradiction in slope at any point along the graph, then we have essentially what we're looking for, right? In terms of differentiability, right? So whenever we're doing this, what you need to do, I'll write the steps here. You first test for continuity. All right, we want to make sure that there aren't any jumps or holes or anything like that. And if there are holes, we want to make sure they're filled in by another piece. All right, then find the derivative of each piece. Evaluate each derivative at the given endpoint. I need to steal some more room here, so all right. And if all those things check out, then you have a differentiable function. If you get failure on any level, then you don't. Right. So that's really all there is to it, because you know the next problem is, you know, we could just use the calculator for that, but the example after that is pretty interesting in the sense that, you know, we are going to learn some shortcuts, but this is one that we're going to want to tackle together. So I'm going to put a star on this one, ask you to have a look at that one on your own. But the next one, I mean, you could definitely try it, because some people know the shortcut rules, but the shortcut rules aren't going to, unfortunately, help you too much on a test when I ask you to do it find the derivative using the limit definition, right? Which is the technique that we've been going over. So hopefully everybody's been kind of focused on that. Focus is the word of the day, by the way. Focus. So yeah, for this one, you could do this on your calculator. You could do this on Desmos. You could do it using a TI calculator. But for this one, we want to do it using limit definition. In fact, before I let you go, let me just at least get you, I'll give you an advanced look at this so that we could get started on it. But I'm not going to do the whole thing. And next class, I'll pick up on it. But if I say f of x.
I'm sorry, Professor.
Yo, what's up?
Can you, what to say test for the number one? It says test for something. I can't read the word.
Test for continuity.
Okay, all right, thank you.
Yeah, no problem. So f of x is equal to the cube root of x. If I want f of x plus h, I'm replacing the x with an x plus h. And so for the slope of the secant, I'd be taking the cube root of x plus h subtracting. One sec, let me just write this real quick, then I'll scroll up. Then a cube root of x, and then all over the h. All right. Just the way the app works, I kind of need to write towards the bottom of the screen just to make things easier. And if it works out, it works out, but sometimes I have to do that, then scroll up after the fact. But yeah, so this is going to be the setup for what we would need to do in order to find the slope of the tangent line. All right. So the slope of the secant is going to involve a process that, honestly, I mean, it'd be great if you knew it. It would mean that you remembered an obscure topic from two courses ago, but you would certainly be forgiven if you don't remember it. But if you want to try to tackle this one, this is the first step in the process. But yeah, we're going to go over this one together on Thursday. All right, so that's where we're going to leave it for tonight. If you have any questions.